Hi everybody, this is Mrs. Ewald again, and welcome to your second podcast for tonight on pH. I'm going to go through this really quickly, so please listen for the whole thing and don't just fast forward. I just want to make sure we are all on the same page. First thing I want to go through is kind of like a heads up for what we're going to be going into with calculations next week, and that is identifying strong and weak acids and bases. So a strong acid, understand an acid, and we were talking about pH. It's all about the amount of hydrogen ion that's in the concentration. So if you have a strong acid, what it means, like for example, hydrochloric, what it means is it's going to completely dissociate when in solution and break apart into its hydrogen ion and chlorine ion. And it's this hydrogen ion, when that's present, it's what makes it acidic. This is the stuff that'll hurt you. And so you need to start memorizing your 6 common strong acids, and Miss Heaton will take you through more of an explanation with your strong acids and how this relates to when we start calculating Ka. But this is just a heads up ahead of time. Make sure you know what your 6 strong acids are. Again, these are the ones that will dissociate completely in solution, so cause the most harm. And a strong base are anything with a cation, like for example, sodium hydroxide or potassium hydroxide. Those are all cations from the first and second group of your periodic table. And so those are bases that would dissociate completely. And so for example, sodium hydroxide would dissociate completely into sodium ion and hydroxide ion. So having a large concentration of hydroxide is what makes it very basic, which again can also harm you very badly as well. Okay? A weak acid or a weak base are things that do not dissociate completely, and so starting next week when we start looking at Ka calculations, we will be able to look at those weak acids and weak bases and do calculations with them. So getting into pH, these are just some key notes, especially after the activity that you did today on the Power of Hydrogen lab. You should remember pH again from biology. So the power of hydrogen, again looking at the amount of hydrogen ion that's in a solution. And so remember from our first podcast tonight that water can behave as both an acid and as a base. And it will dissociate into, or it will break down into hydroxide ion and hydronium ion. And so pH, again, is looking at the amount of hydrogen ion that's in the solution. And so the more hydronium you have, the more acidic it will be. The less hydrogen ion that you have, the more basic it will be, because you will have more of a presence of hydroxide. So the amounts of hydroxide ion and hydronium ion are always equal in water. So what that means is when you have, let's say, for example, in a beaker, equal amounts of hydroxide and hydrogen ion. So I'm also showing this as hydrogen ion, okay? Just because it's a little bit easier to write out. When you have equal amounts of both, you know that you have something that is neutral, having a pH of 7. And so what that means then is the concentration of the hydrogen ion in the solution, it would be 1 times 10 to the negative 7th moles per liter. So it would be molar. Okay? You could also then figure out a few things. For example, if I know my hydrogen ion concentration, I could then figure out my hydroxide ion concentration, because the product of the two equals 1 times 10 to the negative 14th. So if I know my, again, hydroxide, I should then be able to figure out my hydronium ion concentration. If I have one, I should be able to figure out the other using this expression. You may remember acids, the more hydronium ion you have or hydrogen ion you have than hydroxide, the more acidic it will be. Please understand though, the more acidic, it means that you're going to have a lower pH. So a pH of 1 through 7, so right below 7 is going to be, so we'll say 1 through 6. 0.999. Those are going to be acidic. You could also have different ranges. So if you're 1, you're considered to be a strong, versus as you get up here, you're going to be considered more of a weak acid, closer to neutral. Bases, the more hydroxide ion you have, so that really when you're talking about pH, you're saying you have very little hydrogen ion. And so this would be a pH then of anything greater than 7. So anything greater than 7 is going to be a pH that shows you have a base. Now what I want to go through is the fact that the pH scale is logarithmic, and what that means is, let's say for example, we compare a pH of 2 and a pH of 3. So if you have a pH of 2, it's not just one space, so this would be strong acid, and this down here would be strong base. It's not just one step away, it's actually 10 times. So each one of these increments is 10 times difference. So if you have a pH of 2 and a pH of 3, a pH of 2 is 10 times stronger than a pH of 3. And then if you compare 2 to 4, so this is 10 times. When you compare 2 to 4, that's now going to be 10 times 10, so that would be 100 times stronger. So a pH of 2 is 100 times stronger than 4. And if you were to compare 2 and 5, now it's 10 times 10 times 10. So now you're talking about 1,000 times stronger. So a pH of 2 is 1,000 times stronger than 5, and so on. So down here is when you have the most hydrogen ion. As you move down the pH scale then, the closer you get to 14, the less amount of hydrogen ion you have, and the more hydroxide ion will be found. So strong acids are here by 1, and then strong bases are going to be up here by 14. And then you see the range. This here would be neutral. And this is when you have equal amounts of hydroxide ion and hydrogen ion in solution. This would be more hydrogen ion. This would be less hydrogen ion, more hydroxide. Okay? So these are some of the things that you should have taken away from your activity today. And that is pH is power of hydrogen, is how much hydrogen ion you have in solution. These are some different ways of calculating things. You should know that pH is equal to the negative log of your hydronium ion or hydrogen ion concentration. So if I know how much my hydrogen ion concentration is, I should be able to calculate my pH. So if I know that I have 1 times 10 to the negative 8th molarity of hydrogen ion, take the negative log of that, and I would be able to calculate my pH, which would then be 8. pOH then is the negative log of the hydroxide ion concentration. The sum of pH and pOH should equal 14. So if I have a pH of 8, then my pOH is going to have to then be 14 minus 8 in order for me to get a total sum of 14, which makes sense. And then if you are ever given the pH, so again, like a pH of 8, you could then take 10 to the negative 8, which is the pH, to get your, then back to your hydrogen ion concentration. And the same thing too goes for hydroxide. And so just a quick example, there's multiple different ways of solving, going back and forth, using that information, as well as from what you did in your lab today. So if you have a pH of 3.95, I can then calculate my hydrogen ion concentration by taking 10 to the negative 3.95 and end up with 1.12 times 10 to the negative 4th molar. I could also calculate my pH knowing that 14 minus 3.95 is going to equal my pOH, so this would be 10.05. I can then take my hydroxide ion concentration, or solve for that, by taking 10 to the negative 10.05 and end up with 8.91 times 10 to the negative 11. And then how do I know if it's an acid or a base? I look at my amount of hydroxide ion as well as my amount of hydrogen ion. Looking at my two concentrations, I have way more hydrogen ion than I do hydroxide, so that's what makes it an acid. All right, so I just took you through what strong acids, strong bases are. I also took you through pH and what that means, and the fact that it's a logarithmic scale and you go by tens. We also then went through a few of these different expressions to be able to calculate pH or POH or any of that. So make sure you could go back and forth on it. So this is Mrs. Ewald signing out, saying happy pHing.